Hi, a very good afternoon to Madam Aliana and my beloved friends. Today, myself, Sankavi, daughter of Sugumaran, my machine number will be 23 DEM 19 at 1038.
Hi, I'm JAIRAJ Sivakumar.
My name is KANESHA. I'm from class DEM 3B. My matrix number will be 23 DEM 19 F1056.
I'm going to explain about Newton's law of motion. If you see, Newton's law of motion will be divided into three categories, which is first law,
Second law,
and third law.
So my part today will be going to explain about Newton's first law of motion. What is Newton's first law of motion actually? Well, if you see, Newton's first law of motion are also known as law of inertia. I'm going to give a definition for Newton's first law of motion. Newton's first law of motion states that every object will remain at rest or in uniform motion in a straight line unless acted by an unbalanced force or external force net to change its states. What are the examples actually for the Newton's first law? If you see, coin stack tower is a good example and a good experiment from Newton's first law, and also it's explained about the Newton's first law and about inertia too. Whenever we swipe up the stack of coins one by one from the bottom, we can see truly that inertia make the coins, which is from the top of the bottom coin, the top coins, make it fall down because of the inertia. Well, I'm going to take this example as my experiment, and I'm going to explain more detailedly through this experiment about the Newton's first law. Come, let's take a look about this experiment. The apparatus that we need to do these experiments are coins, which all the coins must be in the same size, and also a knife. Steps are needed to do these experiments are arrange these coins into this form, in stack form, and also we need a knife. We can use any type of knife, but I would like to use this type of knife. But whenever you are using this type of knife, be careful with the edges of this type of knife, because the edges of this type of knives are very sharp and need to be more careful whenever you are using it. What we have to do is, we need to swipe the knife like this with enough force. Be careful whenever you are swiping the knife with your fingers. So let's swipe with enough force. We have done our experiment successfully. Now, how this experiment is connected to Newton's first law actually, I will explain to you. You see, the coins are stacked, they are at rest and want to stay that way. According to the first law of motion, if you try to move the bottom coins in the stack, the rest of the stack will want to keep still while the bottom one is removed. Friction or the resistance between objects will try to keep the coins together, but inertia will try to keep the top of stack unchanged. You need to use enough force to move only the bottom coin by overcoming the friction between the bottom and second to last coin so the stack can stay at rest. Overcoming the friction between the coins will halve the force that is moving at rest of the stack, and the inertia will keep the stack at rest. Eventually the coin stack will topple over as the force used to remove the coin and the friction between the coins are more powerful than the inertia present from Newton's first law of motion. These experiments are totally connected with Newton's first law, and you can see clearly which is inertia act in this experiment, and it shows that Newton's first law are truly connected with this experiment.
Hi, I'm JAIRAJ Sivakumar. Today I'm going to present you about Newton's second law. Okay, Newton's second law says that an object of a mass subject to the unbalanced force will have an acceleration in the direction of the force. For giving a mass acceleration of the object will be larger of a larger unbalanced force. To achieve a given acceleration, the force required will be larger for an object with a more mass, represented mathematically in the form of force equal mass times with the acceleration. That means equation for the Newton's second law is F equal to ma. Ma is a mass times with the accelerations. Okay. According to this formula, I'm going to show you about an experiment represent Newton's second law using cars and oil bottles with an empty and with a fill up. So let's go to the experiment. Okay, as shown in the experiment, this is the board and this is the excretion, and I'm going to apply this car. This one is Mercedes-Benz and this one be 007. So this is the car model. Okay, which ones go faster? Is Mercedes-Benz go faster than 007? Because Mercedes-Benz car was more larger than this 007 car. So this is the cause of the object of change velocity to the accelerate. So we need to apply the force to the Mercedes-Benz. So amount of this force to say 007 car and Mercedes-Benz. For 007 car is small force, it's equal to small acceleration. For Mercedes-Benz, double force it's equal to double acceleration. So it means this Mercedes-Benz has a more larger amount of force than 007's car. In other words, how much an object accelerates depends on the mass of the object and how much force is applied. So the equation for this is force equal to mass times with A is acceleration. Okay, I'm going to show you a small example or small calculation about this one. I'll take the largest amount, that is Mercedes-Benz. So this is the Mercedes-Benz car. So before that the car is going down, so the amount of time, so T equal to time, X equal to locations, and V for velocity, and this is the mass. Okay, when the force is going down, the T, X and the V and the M was of 0, so that's not a value. So when the cars go down, it's turned to 1. Times equal to 1, V equal to 1. V means the velocity that's changed to 1. Sorry, this is X. X is equal to location is equal to, because this location is by different, there's a go by different locations, so equal to 1. So the velocity changed to 1, the mass is changed to 1. So in a difference form, F is equal to, that means force equal to M mass 1, V velocity 1, minus with M 0 and V and 0, because it goes to minus with the previous then the replace the car will go down. So have to divide by time, so always by time. So T is the first one that will accelerate, so T1 minus T0 the previous one. So with the construct mass, F equal to M V1 equal minus with V0 divided by T1 equal to T0. So this is simple equation for that to count the accelerations for the speed for car Mercedes-Benz. So this Newton's law apply force equal to mass times weight acceleration. So this is my presentation with using as Newton's second law. Okay, thank you.
Good evening. So today I'll be talking about Newton's third law, and I've come out with an experiment to explain how the Newton's third law is formed, right? So what is Newton's third law? Newton's third law states that for every action there's an equal and opposite reaction. So what does that mean? That means when you are doing something, let's say if you were to throw a ball, there will be another reaction forcing itself on that ball to cause it to slow down. It could be friction, it could be air resistance, it could be anything. So for the experiment, moving on to the experiment, we will show exactly what Newton was trying to explain. A piece of string and also a tin can filled with water. So what we're going to do right now is we're going to poke a few holes inside the can and attach the string to the tab, and we'll see what happens next. So from the experiment, we can see that gravity pushes the water out of the holes from the bottom of the can at a great force. Now, since the holes are angled slightly, we see that the water comes out from a clockwise direction, and because this force is great, it helps push the can along its axis in another direction. This proves that when an action occurs, it produces an equal and opposite reaction, Newton's third law. Other more complex examples for the third law is when a rocket launches and also when a bullet is fired. So, in conclusion, if we were to design a new piece of technology, something that might move per se, we should always keep Newton's laws in mind to help us in the future. Thank you.
Okay, thank you.
And thank you.